Hi there, my name is Andrew Brown, and welcome to Monosaccharide Reactions. This video is going to introduce some of the core reactions undergone by simple sugars on the MCAT, and we'll see a few different renditions of the esterification and glycoside formation reactions. After watching this video, you should be able to handle a question like this one, which tests your ability to identify monosaccharide functional groups and predict the effect they will have on a given chemical reaction. As we know, redox reactions involve the gain and loss of electrons. In sugar chemistry, we can get a rough guess at the level of oxidation or reduction in a molecule by tracking the number of bonds to oxygen versus hydrogen. In the reduction of beta-D ribose seen here, the hydroxyl group is replaced by a hydrogen atom, giving rise to a deoxygenated product. Because the hydrogen atom was added at the second carbon, we term this molecule beta-D2 deoxyribose, the same organic molecule found in DNA. Just as we saw the number of carbon-oxygen bonds decrease in reduction, oxidation reactions will see an increase in carbon-oxygen bonds. When one of the hydroxyl groups in a cyclic monosaccharide is oxidized, a ketone will be formed. If that hydroxyl group resides on the anomeric carbon, we can call the product a cyclic ester. While it isn't necessary to know the exact name of this product, you should remember that any six-membered cyclic ester is termed a lactone. Another functional group commonly tested on the MCAT is the aldehyde. Because aldehydes can be oxidized, a property of a reducing agent, we term aldoses reducing sugars. Benedict's reagent, CuOH2, is commonly used to test for reducing sugars. If a reducing sugar like beta-D glucose is subjected to Benedict's reagent, the result is an open-chain carboxylic acid. When we look at this in a bit greater detail, the aldose produced from ring breakage can be clearly seen being oxidized. Tautomerization is a related process in which a ketose, a non-reducing sugar, can be converted to an enol and then to an aldose, which is a reducing sugar. That concludes the rearrangements and internal reactions that we'll see undergone by monosaccharides in this video. Now I'd like to turn to the substitution reactions undergone by monosaccharides, and the first of which we're going to talk about is esterification. As we're going to see in a little bit, hydroxyl groups often act as nucleophiles in substitution reactions. When beta-D glucose is reacted with acetyl anhydride, the reactant pictured beneath the blue arrow here, we get each hydroxyl group being replaced by an acetyl group. And, as you know, within organic chemistry and biochemistry, functional groups can be represented in multiple ways. The MCAT is going to assume you're familiar with each of the different monikers, which is why we're introducing one, AC, which stands for the acetyl group, here. Now that you've seen how esterification proceeds, it's time to introduce a common example of esterification that's likely to appear in your MCAT, and that is phosphorylation. So just like in the previous example where we started with a molecule of beta-D glucose, this time that hydroxyl group is going to be replaced with a molecule of inorganic phosphate from ATP, which produces the product beta-D glucose 6-phosphate. Just like we saw in the previous example, our hydroxyl group is going to act like a nucleophile and is going to attack that terminal phosphate group in ATP, producing a substitution reaction at the 6 carbon. So in beta-D glucose 6-phosphate, we have now formed a glycosidic linkage between the 6 carbon and a phosphate group. More on glycosidic linkages to follow. So before we explore the mechanism whereby glycosides are formed, I'd like to actually define what in fact a glycosidic linkage is, and then define a few examples that you might see on your MCAT. A glycoside is a molecule that contains a bond between a functional group and one of the carbons of the sugar. That bond is termed the glycosidic linkage. So in the example of isopropyl beta-D thiogalactoside here, don't worry, you can just say IPTG, the glycosidic linkage is the actual bond that joins sulfur to the anomeric carbon. You may be thinking that glycosidic linkages are familiar, and that's because they're the same type of bond that we see in disaccharides and other polysaccharides that join the two monosaccharides. Here in lactose, That is the bond with O in the middle that bonds one molecule of glucose to a molecule of galactose. Now for the mechanism. So here in the picture of a hemiacetal, just imagine that hydroxyl group would be the same as one of the hydroxyl groups from our molecule of beta-D glucose that we saw in the previous two examples. In the first step, an acidic workup allows for the electrophilic removal of a hydroxyl group from the hemiacetal. The subsequent delocalization of charge makes nucleophilic attack by a primary alcohol feasible. And the final step involves the formation of the acetal and the regeneration of our hydronium cation. Now that you've seen the mechanism, we're going to put it all together. A molecule of beta-D galactose and O-nitrophenol will form a glycosidic linkage when the primary alcohol in O-nitrophenol, acting as the nucleophile, interacts with the anomeric hydroxyl group on beta-D galactose, acting as the electrophile. We get a glycosidic linkage formed between the two molecules, forming O-nitrophenyl galactoside, or ONPG. That concludes this video's material discussion. Now put what you learned into practice with a sample question. Here you're being asked about the role of the hydroxyl group in a phosphorylation reaction. The answer is A, nucleophile. Phosphorylation, which is essentially an esterification reaction, involves the nucleophilic attack by a hydroxyl group on a phosphate group. Given the excess charge density on the phosphate group, it is clearly the nucleophile. That makes the hydroxyl group in fructose 6-phosphate the electrophile. If you got that one right, congratulations. If not, please feel free to go back and review as you feel necessary. Before we finish, however, let's review what this video covered. We started with redox reactions and saw the reduction of beta-D ribose to form beta-D2 deoxyribose, as well as the oxidation of beta-D glucose to form a lactone. We then recapped keto-enol tautomerization and how a ketose can be converted back into an aldose. Phosphorylation was shown to be a type of esterification reaction in which a phosphate group serves as the electrophile, and glycosidic linkages were explored, including the mechanism whereby they are formed. Thanks very much for watching, and good luck in your continued MCAT study.